Hello and welcome to this video about rectifier diodes. In this video, we'll learn how to calculate the multi-frequency matrix impedance of a diode in a bridge rectifier circuit. They won't have the same impedances because they'll operate on different cycles. So there'll be two different rectifier diode impedances in this circuit. I've already calculated these impedances using half-wave rectifier diodes, but this time they'll be a lot more accurate. So these are all of the voltages in this circuit. There'll be two diodes that are in the same cycle and are identical to each other, called the D1 diodes, and the voltage across them will be VD1. The voltage across the load is VRC, and the voltage across the voltage source is Vs. So using the mesh law, these voltages will equate to zero. But when we calculate the voltage VD1, we'll have to multiply it by this K term, because there'll be a lot of inaccuracies in its calculation. So the equation should look like this, with a term K that's close to 1, but not exactly equal to 1. And so this will be what the voltage is across the diode, in terms of all these other voltages. We can split this circuit up into having two voltage sources. The second pair of diodes will have a different voltage across them than the first pair. This is the voltage across the load for the bridge rectifier. This is the voltage that we'll be using to calculate the diode impedance. But we're not going to use this current, because this current is split between both pairs of diodes. This is the voltage across the load of a bridge rectifier, the load being a resistor in parallel with a capacitor. This is the voltage we'll use to calculate the impedance of the diodes. And these two peaks are the load current going through both the capacitor and resistor together. The first peak goes through the first pair of diodes, and the second peak goes through the second pair of diodes. So we can't use this current to calculate the diode impedances. Notice that this current isn't very well represented by this graph, because of asymmetry in the calculations. We'd need a much larger amount of samples to represent them well, so we won't use this data to calculate the diode impedances. This is the voltage across the load for a half-wave rectifier. The hump corresponds to the first hump of the bridge rectifier load voltage. And this is the load current for this half-wave rectifier. This is nearly equal to the load current through the first pair of diodes in the bridge rectifier, and so we'll use this current to calculate the diode impedance in a bridge rectifier. We can do a similar thing with the other pair of diodes. We'll calculate the current through each pair of diodes using this half-wave rectifier circuit. This is the voltage across the first pair of diodes. Using the mesh voltage method, we'll get this equation. And so this is the voltage that we'll use to find the current through each diode. And when we flip this diode to be in the opposite direction, we'll get this voltage for the other pair of diodes. So now we'll define the voltage vector for this circuit. It will consist of a DC or constant voltage and an AC voltage with a frequency of omega, and a second AC voltage with a frequency of 2 omega. This can be represented by this equation, needing 5 variables to describe it. We'll use this many variables because the ripple is in the second harmonic, which needs at least 5 variables to represent it. We can pack this equation up into this vector equation, so that we can work with these constants that represent the voltage much more freely. The current can be represented by a similar vector. We did this last time to get the half-wave rectifier diode impedance and a fairly good bridge rectifier diode impedance. We get a large amount of time-sampled voltages using a simulator, and we'll get them for varying values of resistance, while keeping the capacitance constant, so that they'll represent a large amount of resistance to capacitance ratios. We'll then multiply this matrix by a fast Fourier transform matrix, so as to get a large amount of frequency sampled voltages. That should be very accurate. So then we'll only take the first 5 columns and first 5 rows of this matrix to represent this data, This should be accurate enough to work with. And here's an example of such a matrix. Notice that the ripple is extremely low in the first harmonic. It should ideally be 0, but the simulator wasn't accurate enough and didn't have the symmetry to give it a 0 value. The DC values in the first row are high compared to the rest of the values, showing that it's doing a good job at transforming AC voltage into DC voltage. These are the sample values of resistance and capacitance that they were found for. So now we have to calculate the voltage across the diode. We'll use these equations to find it. This is the input voltage, which is a sine function. It is 1 for this row and 0 everywhere else, and is always the same, not depending on the values of the load. So this is what the voltage is across the diode. Its middle row has grown to be this value, which is very nearly equal to 1. So this is the value of VD, which we'll use to find the diode admittance. So now to find the current through this diode called ID, we'll use the half-wave rectifier circuit to find it. The diode current should be equal to the load current. We'll construct the load admittance for each sampled voltage. The admittance for a resistor is this, being a diagonal matrix of the reciprocal of its resistance. It behaves like a scalar real number. And this is the admittance of the capacitor. It has 0 resistance, so it needs to be in parallel with a resistor. The admittances for each frequency behave like complex numbers here as shown. The angular frequency is 1 radian per second, so then the capacitor's admittance simplifies to be this. So to get the load admittance, we'll add these together to get this matrix. And we'll substitute the values for resistance and capacitance into this matrix to get the admittance for each particular load. We'll use a different admittance matrix to get each column of the current through the load. And we've done this here. This is what the calculation of the load current looks like. We can represent it using dot notation here. And this is the voltage matrix that we've calculated using a simulator for a half-wave rectifier circuit. We've calculated it using the same method as for the first voltage, and with varying values of load resistance. We'll substitute all of the values of these matrices into this matrix formula like this. And it will give us this matrix, which should give us columns of load current vectors for each load. This should also be equal to the diode current. So this is how we'll calculate the diode admittance matrix, as current divided by the voltage. So we'll substitute all of these matrices into this equation, which will give us this value for the diode admittance. All of the values are given to 4 significant figures, so that they may be written and seen in this video easily. It should have this term called K, which we decided to use at the beginning, which should be close to but not exactly equal to 1. But we'll find the diode impedance without this value of K first. So we'll try some different values of K and substitute it into the circuit analyzer, which works like SPICE to simulate the circuit. I've already calculated the admittances for the other pair of diodes using the same method. As we vary the value of K, we'll get closer to the DC value given by the simulator, eventually finding the value of K. These are the final values for the admittances. We'll use a similar method to find the admittance for the second pair of diodes, but we'll use a source voltage of minus sine omega t, and we'll use the current calculated from the second half-wave rectifier circuit. Here are some of the calculations used to find the second diode admittance. And here are some more of these calculations, so that you won't get confused if you try to duplicate these results. We'll calculate the impedance values for these diodes by finding the inverses of these admittance matrices. And here's the impedance of the diodes in the second cycle. Now to look at the results to see how well the circuit model of these diodes compares to the simulated expected value. All of these numbers look very good. The DC values look extremely close. The AC values look good too. We need to process this data to get a better look into how good this circuit model is. And here are two more load impedances to look at and compare results for. So now to process this data to see exactly how well this matrix impedance model works. We'll compare the circuit output with the output from the simulator. Firstly, we'll calculate the magnitudes of the AC voltages. Then we'll find the ripples being the ratio between the magnitudes of the AC to the DC voltages. We'll find it for each frequency. Then we'll do all of these comparison calculations to see how all of these numbers compare. Ideally, these three numbers should be as close to zero as possible. And these are the two new voltage vectors that we'll calculate for each different value of load resistance. So these are the two voltage vectors for the 100 ohm load resistance. We can calculate the magnitudes of all the AC voltages. Then we can calculate all of the ripples. Then we can properly compare the circuit model with the simulator model. So these are all of the values of the new vectors. We'll look at the comparison vector CP. The DC value is 0, which is extremely good, but we did design it that way. The first AC harmonic is fairly large, but the numbers themselves are small, so that we can get away with it. The last number, which is the value of the ripple, which should be non-zero, is actually quite bad, being approximately 17% out. But we can get away with it because it is small and not really bad, like 10 times as bad. So here are some more of these vectors for other load resistances. The numbers seem to be similar. The last DC value is starting to diverge, but is still extremely good. And here are some more of these vectors for some other load resistances that are further from 100 ohms. The value circled in red is fairly bad, but we can still get away with it, because it isn't too bad compared to the other first harmonic ripple values. And here it is for this last load resistance. Its AC comparison numbers are better than for the 85 ohm case, in the case of the first harmonic ripple. So here are all of the comparison vectors set out to measure the accuracy of this diode model. It seems to work fairly well, but we could do better. But it seems to model the behavior of this circuit well enough. So here's the problem. The load voltage of the bridge rectifier isn't equal to that of the half-wave rectifier at this position, which could cause inaccuracies in the model. The voltage starts to rise at a slightly earlier time in the half-wave rectifier than in the bridge rectifier, which could be causing the inaccuracies. So I hope that you have found this video helpful and interesting. The math can become very overwhelming and confusing because it's very groundbreaking. I haven't seen it done anywhere else. So I hope that it hasn't bothered you too much. Please click like and subscribe if you found this video helpful or interesting. Please leave some helpful thoughts in the comments. Feel free to share this video, and thanks a lot for watching.